We are going to walk through an example of a correlation in this lecture. So we will calculate Pearson's correlation coefficient, or Pearson's R, and then also calculate the corresponding t statistic that will allow us to determine if Pearson's R is statistically significant. This example is an example of a recent study, it's fictional, that wanted to know if there is a relationship between how often people cry or how easily a person reports that they cry and their tendency to fall in love. So in this example, each subject rated themselves on how easily they fall in love and how easily they cry. And on both scales, there was a range of 1 to 7 for response options, with 1 being not at all and 7 being extremely. So each individual has 2 scores. They have an X score and a Y score. The X score represents the tendency of falling in love, and their Y score represents the tendency to cry. So you can see that we end up with 10 pairs of scores, and those are all listed down here. And remember, the format of those pairs is X, Y. So the first individual has a 4 on the tendency to fall in love scale and a 2 on the tendency to cry scale. And the question is there a significant relationship, or is there a relationship at all? And then is it significant between these 2 variables? Remember that one of the first things we might like to do with our data is plot it if we're looking to see if there's a relationship. So this is a scatter plot of these 2 variables. And looking at this, it looks like maybe there's a little bit of a linear relationship, right? Maybe I could draw a line through the points that looks something like this. If there is a relationship, it doesn't look to be a very strong one because those points are spread out quite a bit around this line. But it does look like a relationship, and do you think it's positive or negative? Because this line is increasing across the x-axis, then it is a positive relationship. So let's look at our hypotheses for the correlation. The research hypothesis here is that there is a relationship between the variables, or in other words, that the tendency to fall in love is related to the tendency to cry. The null hypothesis is that there's no relationship or no correlation between these 2 variables. Okay, so here's a whole bunch of numbers. Let's break this down. I have my tendency to fall in love raw scores over in this first column. That's all the information you would be given for this variable. And I also want to draw your attention to this part of the slide over here, which is where we ultimately need to get. So I need to be able to calculate a z-score for this variable for each person. So the pieces of information that I need to glean from the raw scores are X, that's easy, that's what's given to us, those are the raw scores themselves. I also need M, which is our sample mean, and I need the sample standard deviation, which is sum of squares over n. So let's start with calculating the sample mean and get that out of the way. You can see that I've done that down here at the bottom of the first column. If you add up all those scores, we get 43, divide by 10, which is the number of scores, to get a mean score of 4.3. So the average tendency of falling in love score for this sample is 4.3. Then we can calculate deviation scores, and remember deviation scores are x minus m for each person. So for person 1, this is 4 minus 4.3, and so on. The third column is squared deviation, so that's the previous column square, so just the square of negative 0.3 for the first person gives us a squared deviation score for person 1 of 0.09. So the sum of squared deviations is right here. The sum of the column is 32.1. Remember, this is SS. So the sum of squared deviations, also called SS. So the variance of this sample is sum of squares over n, gives us 3.2. That's sum of squares over n gives us the variance. And then we just take the square root of the variance to get standard deviation. So our sample standard deviation is 1.79. So now we have all the pieces to calculate the z-score. So the z-score for each person is x minus m over standard deviation. So for person 1, we get negative 0.17, and that comes from taking their x-score 4 minus m, or 4.3, and then we divide by 1.79. And just a hint to make this a little bit faster for you, notice that you've already calculated x minus m for the numerator of the z-score. So for person 1, I can just plug in negative 0.3, that's their deviation score, over 1.79, the standard deviation. For the third person in our sample, who started with a raw score of 5, we calculated their deviation score already, which is 0.7. That's the numerator of their z-score, so 0.7 over 1.79 gives us a z-score of 0.39. So you calculate a z-score for every person in your sample for the x variable. Then we come over here and we do the exact same thing for y. So again, I'm not going to work through this one step by step, but you could try to reproduce everything I have in this table. And the goal, remember, the reason we're calculating all these values is to be able to calculate a z-score for each person. So we needed the sample mean, and we needed the sample sum of squared deviations to get to standard deviation. So then we end up with our z-scores for the y variable for every individual. Okay, and I've just combined that information onto a single slide. So we just calculated all the z-scores for x and the z-score for y, and we multiply those together to get cross products. Zx times zy is the cross product. So every person has their own cross product. Then we can take the sum of the cross products. If we add those all up, we get 3.39. Remember, this is the third step in calculating the correlation coefficient. So that's why I calculated the sum of the cross products. So that's the numerator of Pearson's R. The next step, or the final step, is to divide by n, as you just saw in the previous slide. So 3.39, the sum of cross products, divided by sample size, which is 10, gives us a Pearson's R value of 0.339. Now, how would we describe this correlation? That's a great question. This correlation is positive because it's actually a positive number. It tells us that the relation between these two variables is positive. So there's a positive correlation between the tendency to fall in love and the tendency to cry. Also, we see that it's closer to 0 than it is to 1, but it's not tiny. It's not very close to 0. So it's about 0.34, and I would describe this as a moderate size correlation. And there are particular cutoff values that we tend to use in social sciences and specifically in psychology, and you can find those in your textbook. But you'll find different rules when you look in different resources. So there's not a single agreed upon cutoff value for what is a small, what is a medium, and what is a large correlation. But we tend to think of anything above 0.5 or 0.6 in psychology as being a pretty decent sized correlation, pretty large correlation. Anything in the range of about 0.3 to 0.4, 0.5 being a moderate correlation, and something smaller than that being a small correlation. So like I just said, this is a moderate positive correlation between the tendency to fall in love and the tendency to cry. But then I might ask myself, is it statistically significant? Is this value of Pearson's R a value that is high enough that I think it would be very unlikely under the null hypothesis? And if so, I would like to reject my null hypothesis and say I have evidence or support for my research hypothesis that there is truly a relationship between these variables. So if I actually want to do that statistical test, I need to calculate a test statistic. And the test statistic I'll use is t. I'm using a different formula for t than the one you've seen previously, and that formula is here. So notice that we just need to plug in our Pearson's R value that we've just calculated, and we need to know our sample size. So remember, our sample size was 10, and I'll round our Pearson's R to 0.34. So if I plug those values in, I have 0.34 in the numerator, and then in the denominator, it's all under a square root sign. I have 1 minus 0.34 squared divided by n minus 2, or 10 minus 2. So finally, that reduces to 0.34 over 0.33, or a t-value of 1.03. So this is my sample t-value, and I want to compare this to a critical cutoff score that I can find in my t-table with degrees of freedom n minus 2. So I'm doing a two-tailed test. For now, with correlations, just always assume you're doing a two-tailed test. And the researcher can determine what significance level they want to use. Let's use 0.05. And degrees of freedom is predetermined. That's n minus 2, or in our case, 8. So I'm using 0.05, degrees of freedom 8. So if I come over here, play my little battleship game, I get a critical cutoff score of 2.306. So that means anything that is beyond negative 2.306 or above positive 2.306 or above positive 2.306, then I would reject my null hypothesis. My t-score is 1.03. So my score is not more extreme than the critical cutoff value, which means that I failed to reject my null hypothesis, and I do not have support for the claim that there is a significant relationship between the tendency to fall in love and the tendency to cry. So basically, this means that though we've detected a moderate correlation between the variables, our statistical test is telling us we don't have strong enough evidence to claim that this relationship exists at the population level. So it doesn't mean that it doesn't exist, just that in our study, we don't have very strong evidence that that relationship exists. So maybe we would want to be cautious about drawing inferences to the population level when it comes to our sample findings. And that's the end of this lecture. Let me know if you have any questions, as always.